Welcome to the third video in Rotation and Torque. In this video we will be looking at how we can move between translational or rotational motion, so the relationship between the two. So I'd like to start by looking at the velocity, as it's slightly out of order, but the reason should hopefully become shortly apparent. So if we look at our yellow oval undergoing uniform circular motion, and we look at just one point on that object, so I'll define that for the moment as this purple point here. And we know because in rotation we're dealing with rigid bodies, then that means that the distance from the axis of rotation doesn't change. So as our yellow oval rotates about its axis, this single point, this purple point, describes a circle about the axis of rotation. So that is, this single point as part of the larger object is undergoing uniform circular motion. And we know how to deal with uniform circular motion. We know that our object is moving with a velocity v equal to the displacement over time, or the speed is equal to the distance over time. And we also know now, both from uniform circular motion but also from the first video in the rotation topic, that our angular velocity is equal to the angular displacement divided by the time. And to get an equation for the velocity, we'll look at what happens in one revolution. So in one revolution, the time that's passed we call capital T, or which in uniform circular motion was our orbital period. And we know that in one revolution, we travel the circumference of a circle radius r, which is 2 pi r. We also know that we cover 360 degrees, so our angular displacement is 360 degrees or 2 pi radians. Substituting those values into our equations for the velocity and the angular velocity, we find that our velocity is 2 pi r on t and our angular velocity is 2 pi on t. If we combine those two equations, we get the relationship between our velocity and angular velocity as v equals r omega. So all three of these equations should come as no surprise, since we've already dealt with them in uniform circular motion. In this case, our angular speed, our velocity, is in meters per second, our radius is in meters, and our angular velocity is in radians per second. In this last slide, we'll just look at the relationship between the position and the angular position, followed by the acceleration and the angular acceleration. So looking for an expression relating our linear position to our angular position, we again take the position of our purple point, and we know our purple point is some radius r from the center of rotation, and that radius r is the radius of its uniform circular motion. So we saw in our first video that our angular position is described as s divided by r, where s is our arc length and r is the radius to that arc length, so the radius of that arc. So in this case, we choose our arc length to be the part of the circle that our point describes, and that gives us that our radius is then our purple arrow. So it's then the distance of the point we're looking at to the axis of rotation. So rearranging that, we find that our position s in meters is equal to theta in radians times the radius of our orbit, or the radius of the orbit of our point of interest in meters. And the last thing we'd like to try and relate is the acceleration. So we know that our acceleration is given as the change in velocity over time. And we saw in the previous slide that our velocity v is equal to r omega. So that means our acceleration in meters per second squared is equal to the rate of change of r omega. Our radius is a constant, so that gives us the rate of change of omega. And we know that the rate of change of omega is the angular acceleration. So our linear acceleration in meters per second is equal to our angular acceleration in radians per second times our radius in meters. Now, we need to be careful here. So we've used the formula v equals r omega to describe our acceleration. And v equals r omega is our tangential velocity. So what we've just found is the tangential component of our acceleration. And what that means in real terms, that's the acceleration that describes the change in the velocity magnitude. But it doesn't have anything to say about the direction of the velocity. So in order to find the complete acceleration, we also have a second component that describes the changes in the velocity's direction. So we know from uniform circular motion that the change in the velocity direction is caused by the centripetal force. So that means the acceleration which describes that is the centripetal acceleration, which is equal to v squared on r. And once again, we know that v is our omega. So if we substitute that in, we find that our centripetal acceleration is equal to r times omega squared. And that's the radial component of our acceleration. And those four equations describing our velocity, our position, and the two components of our acceleration are all we need to be able to relate our translational motion that we're used to, that we've used before, to our rotational motion.